First, some Lewis structures. C3H8 propane. So you got 3 carbons and 8 hydrogens. Each of the carbons has 4 electrons, each of the hydrogens has 1. And there aren't a whole lot of choices here, as you probably found. If you try to hook them up in like a triangle, you actually can't get enough hydrogens on there, because now you've put 6 on and all the carbons have full octets, so you can't put any more on, right? So that doesn't work. So the only way that actually works is if you have it kind of in a straight chain with each carbon surrounded by hydrogens, kind of like in the line structures. So a line structure of that would be like this, or you could have drawn it straight across as a Lewis structure like this. And there should be no non-bonding electrons, double, triple bonds, anything like that. Good? Okay. Next one, O3, ozone. You got 3 oxygens. And again, you have to have enough electrons. So in this case, the way to do that is like this. If you try to connect them in other ways, you'll probably find that there are not enough electrons to go around, or you have more than an octet on a given atom. For instance, if you try to do it like this, what's wrong with that? Too many in the middle. That middle oxygen has 2, 4, 6, 8, 10 electrons, so that breaks the octet rule. So that won't work. What about if you did it like this? Right, in this case I added some electrons that weren't there to start with, right? Because if this looks okay the way I've drawn it, but there actually aren't enough electrons. If we start with 3 oxygens, they have 6 electrons each, right? So that means there should be 18 total electrons in bonds and free pairs. This one gets 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So there's actually too many electrons. If you built it up from the individual atoms like this, you probably wouldn't make this mistake because you wouldn't have enough electrons to connect to stuff. Let's try that. I think this does work actually also. Yeah, that also works. This is the actual structure, but this also works as a reasonable Lewis structure. What? What? Yeah, it doesn't occur in nature, but you know, from a paper standpoint, yeah, it works. What? Here? I don't think you can without getting too many electrons somewhere. Like this. Now each of these oxygens has 10 electrons. 2, 4, 6, 8, 10. Well, but remember you have to start with the right number of electrons here. 6 for each oxygen. So you can't just take them off and make them disappear. But this way does work. All right, let's talk about the combustion of propane with oxygen gas. So you got propane and oxygen gas, which remember is O2. Oxygen is always dimer. And that produces carbon dioxide and water. Is that balanced? No. What do you have to do to balance it? Well, let's do it systematically we don't want to balance oxygen first because there's two different things that have oxygen here. So we want to pick one where it just exists on one molecule on each side. Like carbon, we got 3 here, only 1 here, so we can put a 3 out front, and then there's 3 carbons on each side. Then we'll try hydrogen. You got 8 here, only 2 here. So we're going to put a 4 out there, and then there will be 8 on each side. And then we'll look at the oxygen. So right now we have 2 on this side, and then 6 here, and 4 here, which is 10 overall. Yeah?
So is it propane to CO2 a 1:3 ratio?
Yes. Yeah. And that means we need 5 oxygens here. Okay. So if we start with 2 moles of propane, how many moles of carbon dioxide are produced? 6. Because you're producing 3 times as many molecules of CO2 as you started with these. That's the 1:3 ratio. So that's 6 moles. Molar mass of carbon dioxide, you got 12 from the carbon, right? Plus 16 from the oxygen, and there's 2 of those, right? So that's 44 grams per mole. So 44 grams in 1 mole. Okay. And then we use those 2 numbers to come up with part D. If we start with 2 moles of propane, how many grams of carbon dioxide are produced? Well, we know we produce 6 moles, so what we have to do is turn moles into grams. And we use this other number, which tells us the relationship between grams and moles in carbon dioxide to do that. So the way you can do this is you start with moles. We know we start with 6 moles. And you multiply it by a conversion factor, where things on the top and the bottom cancel each other out. So whatever you want, you keep on the top. Whatever you don't want, you put on the bottom. We don't want moles, so we put mole on the bottom. We do want grams, so we keep grams on the top. And this number tells us it's 44 grams in 1 mole. All right. And you do that, I believe you get 264 grams of carbon dioxide. Did I do that math right? Okay. Questions about that? Yeah. Yeah, that's usually how it works. It's easier when you see the answer than when you have to do it yourself. But again, I encourage you to look at those problems in the book, and I'll get some more practice stuff up too, so you can be prepared on this before the exam. From up here. So if we start with 2 moles of propane, that's the same we started with up here, and it's a 1:3 ratio, so we still form 6 moles. Yeah, good question. Other questions? Yeah.
I did like the 2 moles first, and then did the convert, like did it. I got the same number, but I set it up differently.
Okay.
So as long as the answer's right.
As long as it works, yeah.
Okay.
Yeah, if we sort of
I did something with like 1 mole, and then I multiplied it times 6.
Yeah, let's go through that. So we sort of just went through that quickly, like, oh, you start with 2 and it's 1:3, so times 3 and you get this. Let's do it systematically, like step by step. So what you're really doing is the same kind of conversion as down here. You're saying 2.0 moles of propane, and you're multiplying that by the ratio that you see in the equation. And the ratio in the equation is 3 moles of CO2 per 1 mole of propane. So you're doing the same kind of thing as here. You're canceling moles of propane and ending up with moles of CO2. And this is the ratio that we get from the equation. 3 of this to 1 of this. So in doing that multiplication, then we get 6 moles of CO2. So if the numbers get more complicated, like 5 to 3, that's not as obvious, right? You can't just say, well, multiply it by 3 or divide it by 2 or something. If I said 2 moles of oxygen, how many carbon dioxide? You'd have to multiply it by 3 over 5, because that would be the ratio of CO2 to oxygen. So is that sort of how you did it?
That wasn't the question I was talking about.
Oh,
I was
okay.
talking about V. It's fine.
Okay. Okay.
It's still, I still got the same answer.
All right, then you're probably okay. Okay, other questions about this? Yeah.
What if we just wrote the answer?
That's fine. All right, let's talk about energy. This is going to be really important in the next coming weeks, especially after the exam. We're going to, well, next week, not next week, a couple weeks, you're going to talk about batteries, and then we're going to start talking about greenhouse gases and energy production. So energy is going to come into all this stuff. So today is like the very basic stuff. And here's a question that I don't think anybody's going to be able to answer, but I'm going to try. What is energy? How do you define energy? What makes you go? That's actually a really good definition. Well, okay, so if you don't want to think about it in a strict definition, I'll give you the official definition in a minute. But what do you think of as energy? What does energy mean to you? Food?
Nothing that I have.
What?
Nothing that I have.
Nothing that you have. Okay. What else? Heat? Exertion? Yeah, all of these things. The technical scientific definition of energy, should I get this here? Okay. It's the ability of matter to do work. So what makes you go is actually a pretty close approximation of that. Energy is not matter. Matter has mass. It occupies space, right? It's made up of atoms. Energy is not. Energy is the ability of that matter to do work. Now, work can mean a lot of things. Work can mean heating something up. It can mean pushing something. It can mean expanding something, pulling something, all kinds of different ways that we can define work. But that's the general idea of what energy is. Of course, we need energy. We need to take in things so that we can have energy, the capacity to do work, like moving our legs or our heart or whatever. And then our devices need energy so they can do their work, moving electrons around through the various thingies that they have. So that's, I guess, not very technical. What is the unit of energy? How do we measure energy? What are some units? You dealt with one of them on Tuesday. Yeah, so you got the calorie, you've got the joule, all right. What? BTUs, yep. Mm-hmm. British thermal units, we'll say BTU. Then you have also, do you talk about the difference between little c calories and big C calories on Tuesday? Yeah. What you measure in the lab, what you measured on Tuesday, is a little c calorie. That's the amount of energy it takes to raise 1 gram of water 1 degree C. So it takes 1 calorie to raise 1 gram of water 1 degree C. There's also big C calorie, which is what you see listed on food containers. This is actually a kilocalorie, which is 1,000 calories. Little c calories. So when we talk about food calories, when we say, you know, a can of Coke has 150 calories or whatever, we're talking actually about kilocalories, or big C calories. It's less confusing in other countries because they actually report that as kilocalories, so you don't have the same word, kind of, just with the capitalization being the difference. And then there are some other energy units that we use also. Joule is the SI unit, the International Unit of Energy. So that's what's measured in a lot of scientific situations, a lot of things like that. But I don't know if you thought about this at home, but how is home energy measured? How is the energy that you use in your house measured? Do you know?
Kilowatt hours.
Kilowatt hours. So that's a strange sort of measurement. Kilowatt hours. What's a watt? You know? Close. Yes, but
It's like, so volt is a potential, is a measurement of potential energy, and amps is a measurement of.
right. So in terms of what we're talking about here, a watt is 1 joule per second. So exerting 1 joule of energy each second is 1 watt. Think about something like a light bulb, a 60-watt light bulb. What that means is each second that light bulb takes 60 joules of energy. Okay. So to measure power usage, watt is actually a measure of power, not energy. Power is energy per time, as you see here, per second. So to measure how much energy you're actually using, you have to know the power of the device and then the amount of time you're actually using it for. And that's what a kilowatt hour comes from. So a kilowatt equals 1,000 joules per second. And then if you multiply that by 60 seconds per 1 hour, a kilowatt can also be represented as 60,000 watts per hour. So a kilowatt hour actually then cancels out the hours and just leaves you, whoops, I'm sorry, not watts, joules. Just leaves you with joules. So a kilowatt hour actually equals 1,000 joules, or a kilojoule. Or wait, no, I'm sorry, that's not right. That's right, I forgot the minutes, so that's not right at all. There's not 60 seconds per hour. There's 3,600 seconds per hour. So that's a very big number, right? That's 3,600,000 joules per hour is 1 kilowatt. So a kilowatt hour is 3,600,000 joules. Or we could say 3.6 megajoules. It's a lot of energy. Okay, so those are some of the quantities. And one of the things that you're going to be able to do is actually interconvert among these. So one of the things that's confusing about energy is because we have all these different units, when you're looking something up, let's say you want to compare fuels, compare how dense a fuel is or how much energy a gasoline has versus a biodiesel or a ethanol fuel or whatever, you might find one number reported in joules and another number reported in BTUs and another number reported in calories. And in fact, you're going to find all that when you start answering these questions about the biodiesel project. And so you have to be able to convert among these different quantities, and we'll talk about that when we get there. But let's talk a little bit more about energy in chemical reactions. So first of all, the measurement of energy. Did you talk about this at all on Tuesday, or did you just kind of do it? Did you get to see a real bomb calorimeter? Did I show you that? Drew a picture of it? Okay. You'll use those in another week or two, the week of the exam, when we do the analysis of the biodiesel. But the idea is that whenever some chemical reaction occurs, heat is either transferred from the surroundings into the reaction or from the reaction into the surroundings. And we call that the system. So you can imagine here's your reaction or your measurement or whatever, and then everything around it is the surroundings. And when energy is involved, when energy is transferred, we have a couple words for that. If energy goes from the system out into the surroundings, we call that exothermic. And if energy goes from the surroundings into the system, we call that endothermic. So let's look at some examples. Combustion as an example. Right? You burn something. Is that exothermic or endothermic? Exothermic, because the energy flows from the stuff that's burning out into the surroundings and it feels hot. Right? So that's kind of a good shorthand for what's happening in a particular process. If it produces heat that you feel, that means the heat is going out into the surroundings, and it must be exothermic. If it takes heat from the surroundings into it, then it must be endothermic. So something that's endothermic will actually make the things around it get cold. Can anybody think of an example of that? Yeah, like one of those chemical cold packs. Have you seen those? Where it's just a room temperature thing, and you break something inside it, or you mix something up inside it, and then it gets cold, so you can put it on your head when you fell down and hit the table, because, I don't know. But that's an example of an endothermic reaction. You're sucking heat from the surroundings, and therefore it feels cold. The surroundings are feeling cold. Actually, the most important thing about this, you should know these words, but also you'll notice that heat is only ever is transferred from one place to another. Right? So energy isn't created nor destroyed, and that's known as the first law of thermodynamics. Energy cannot be created nor destroyed by a chemical process. Only transferred. So you can only move energy around. You can't get rid of it. You can't create it out of nothing. This rule gets stretched a little bit when we talk about nuclear chemistry, but we'll get into that when we get into it. So energy is always transferred, neither created nor destroyed. Okay. What is a law, by the way? Why is this the law of thermodynamics? What does it mean to be a law? No, doesn't mean it's proven. Not even that. Remember, law is not a degree of certainty. Yeah.
It's a set of observations.
Right. It's a set of observations. Okay. And a law, there's no hierarchy of law and theory. They're different. They can both be proven or disproven. They both need evidence, and they can be shown to be false over time. A law is a set of observations that doesn't try to explain the reason behind it. and a theory is the reason behind it, or attempts to explain the reason behind it. So the law of thermodynamics is simply a set of observations that in every instance that anyone has measured, energy is not created nor destroyed in a chemical reaction. Which brings us to the second law. Let me get the actual wording of this one. The second law is a little bit weird. It says that the energy available for work is always decreasing. Now, that doesn't mean that energy is being destroyed, because that was that would violate the first law. But it does mean that more useful forms of energy always get converted into less useful forms of energy. Or in other words, you can't break even. So if you have a fuel, you burn that fuel, you can't then magically get it back and use it again. It's done. It's in a less useful form now. You have to put more energy in than you can get out, is really what that's saying. Okay. Think about a car. Right? A car has fuel. You put the fuel in, you drive for a while, you use up that fuel, now you need more fuel. You can't take the exhaust from your car and have it become fuel again without putting more energy into it. So that's all this is really saying. Energy flows downhill. If you have, another way to think about this is if you have a hot metal block and you put it next to a cold metal block, what happens? Yeah, the heat's going to transfer from the hot block to the cold block until they're the same temperature. You can't go the other way around. Even if the cold block is only a little bit colder than the hot block, it's never going to transfer its energy from the cold to the hot to increase the amount of useful energy in the hot block. Okay? So you're always kind of moving to a state of lower energy. The universe tends to lower energy. So chemical reactions that are spontaneous because you have a lower energy system when you're done. The energy has been transferred from the system to the surroundings. If you want to transfer energy from the surroundings to the system, you usually have to put some sort of energy in to do that, if it's a exothermic process. Right? We talked about that. Okay, so that's kind of some of the theory about this. And then there's one last piece that we should talk about with energy, which is entropy. Has anybody heard this word before? What is entropy?
Okay, it'd be like you have a very ordered structure,
Mm-hmm.
and then it becomes more disorganized. Or it just changes. There's like so many different arrangements that you put this room into, so over time it would go through every single configuration.
Okay, yeah. Entropy is another way of measuring energy based on the disorder of a system. The disorder or randomness. So think about it this way. You take a bowl of water. I could have done this, but I didn't get it so ready. You take a beaker full of water, and you drop a drop of food coloring in it. What happens? The water, if you let that sit for a day, you'd come back and the water would be, let's say, green, right? So the molecules from the food coloring will dissipate throughout the water. But that's not necessarily, it seems obvious, but why would that happen? Why doesn't the food coloring simply stay in its food coloring ball at the top of the water? Why does it dissipate and become as random as possible?
Because it's a liquid. So I mean, the molecules are moving constantly.
Sure, but why should they move? Why should they go to the more random positions? Why not the more ordered positions? Well, that's why it's a law, right? Because I mean, there are theories behind that, of course, but what we see is that the universe tends toward disorder. The lower energy state tends to be less disorder, tends to be more disorder. So we say higher entropy is more disorder, is lower energy or more stable. So when you put that green food coloring in the beaker full of water, it dissipates, right? And that's because the dissipated randomized molecules through that water is a lower energy state than the molecules all stuck together in a little ball of food coloring. Now the corollary to this is the law, it's actually the third law of thermodynamics, says the entropy of the universe is always increasing. The disorder always has to be increasing. That doesn't mean that the entropy of every single little chemical process always increases. For instance, if you have two molecules, molecule A and molecule B, and they do a chemical reaction to form a compound AB, this involves a decrease in entropy because you've gone from two particles to one particle. So two things floating around randomly is more disorder than one thing stuck together. So you've actually decreased entropy here. However, if this reaction is spontaneous, what you've done then is increase the entropy of the surroundings, of things around it. So you don't always have to increase entropy in every little system, but the overall everything will tend toward greater entropy. You could think about also, so let's say I have a skunk. I'll bring a skunk in next week if you want. Just try to trap one or something. Not really, I'm not going to do that. But I put it over here, and it sprays the door. What's going to happen to the rest of the room? It's going to smell, right? That's, again, because of entropy. That smell doesn't stay contained. It dissipates, it finds more disorder, and it ends up going through the whole room and probably the whole chemistry department. And yeah, my dog got sprayed by a skunk a couple of years ago. It took like a month to get the smell out of the house. So again, that's entropy, this idea that things tend toward greater disorder. It's also, well, we'll get into that another time. So let's look at chemical reactions and how this works in a chemical reaction. Find a good one here. Let's talk about combustion again. Combustion of methane, we've seen this before. Methane, CH4, plus oxygen leads to CO2 plus H2O. Is that balanced? No. What do we need to do? Okay. There we go. So this describes all the chemistry of this reaction. It describes it fine. But we're actually missing a piece, and that's the energy piece. So this reaction involves 803 kilojoules of energy per mole. Which side does the energy go on? In other words, does the energy used up by the reaction, or is the energy produced by the reaction, transferred to the surroundings? Transferred to the surroundings, right? Because the burning of methane would make things around it hot. So we can actually put in another term here that says that there are also 803 kilojoules of energy that are produced by this reaction. Now, in a chemical equation, we don't always show the energy. We don't always care. But it's important to note that it's actually there. And another thing we need to note is that this unit is actually kilojoules per mole. So for each mole of methane that is combusted, we produce 803 kilojoules of energy. This is going to be important also. Well, you did this actually on Tuesday. You realize that the amount of energy that you produce by burning a sample of food changes depending on the size of the food. So for comparison's sake, how did you standardize it? In other words, you had many samples of your food that you burned, right? And they were all slightly different size. So the energy was a little bit different each time. So you standardized it by mass, right? You divided everything by grams. And that way you had a energy per gram measurement rather than just an energy measurement. Yeah. And that's the same thing that we do with these sorts of things. So the combustion, so here's how this works kind of in problem form. I could say that the energy involved in a molecule of propane combustion gives you 2,201 kilojoules per mole. I'm just telling you that from the numbers I looked up. The question then is how much energy can be produced from 50 grams of propane. So you look up the energy on a table and you find that combustion of propane is 2,201 kilojoules per mole. But what you want to know is, I can put 50 grams of propane in a little tank. How much energy can I actually get out of that? How much energy can be produced? How do you do that? Right, well first we have to realize that there's a disconnect in our units here. Our number is reported in kilojoules per mole, but what we actually have is grams. So the first step is going to have to be to convert grams to moles. And we do that through the molar mass. So the molar mass, or molecular weight, of propane, we just talked about on the quiz. What was it, 44? 44 grams per mole. And we're going to do another one of these unit conversions. So we start with 50 grams, and we multiply it by 44 grams per mole, but we need to make sure that grams are on the bottom, moles are on the top, so the grams cancel and we're left with moles. So grams down here, moles down here, and we've got 44 grams per each mole. That's what this number tells us. So we sort of flip that. So in essence, what we're doing then is dividing 50 by 44. You get, what, 1.1-ish? Let's say 1.1. (1.1 mole of propane). And then we can multiply that by the kilojoules per mole. So then we can say 1.1 mole of propane times 2201 kilojoules per 1 mole equals about 24, 21 kilojoules, something like that. That's about right. It's a little early for math in my head sometimes, but we'll get close anyway. So we go grams to moles, and then we use how many kilojoules per mole to figure out kilojoules. So let's see if you can try one, and then we'll take a little break. Come back and talk about fuels. Here is the production of silicon carbide, which is an important material. SiO2, silica, is heated with carbon and 624.7 kilojoules. And that's going to form silicon carbide and CO2. And the question is, well, let's do a couple questions. Let's say we start with 0.10 moles SiO2. I'm going to ask you two questions. First, how many moles of silicon carbide are produced? How many grams of silicon carbide are produced? How much energy is either used or given off? And is it exo or endothermic? So the first thing you got to do is balance this equation and then work on those questions. So work together with people around you and see if you can come up with those using the same techniques that we've just done. First of all, was this equation balanced? How did you balance it? You need two of these. Is that it? I think that's it, right? Yeah. Okay. So we start with 0.10 mole silicon oxide. How many moles of silicon carbide are produced? How'd you figure that one out? Yeah, you've got a 1-to-1 ratio. One of these molecules becomes one of these. So that means that if we start with 0.1 of these, we end with 0.1 of these. Same amount. Okay. What about grams? How do you figure out the grams of silicon carbide? Right. We'll take the 0.10 moles times the molar mass, which we add up 28 for silicon and 12 for carbon. That gets us 40. So 40 grams per 1 mole is 4 grams. Right? Okay. And then how much energy? Again, this is actually kilojoules per mole because it's reported in the equation. So if that's per 1 mole, and we actually have 0.1 moles, we have to do the same type of conversion. We have 0.1 mole times 624.7 kilojoules per mole, and that's 62.47 kilojoules. And then is the reaction exothermic or endothermic? Why endo? Yeah, the energy has to be put in. You see how it's in the left side of the equation? It's like with the reactants. It's being put into the system. So if the energy has to be put in, that means it's taking the energy from the surroundings, and that's endothermic. Compare that to the previous one up here, where the energy came out at the end, and that's exothermic. All right. Take a 10 minutes or so. We'll come back and talk about changes of state and some fuels, and then we'll be all set. So the other part of measuring all of this is, of course, the calorimetry that you've already done. So you did that, but I want to remind you of this equation because it's actually important. Oops. Close. You've seen this equation on Tuesday? No? Okay. This is heat. Q is the variable for heat. Sorry, it doesn't make a lot of sense, but it is. Mass, heat capacity, and this whole thing is delta T the change in temperature. Okay, so this is how a calorimetry experiment is done. And this is, knowing or not, this is what you did on Tuesday. You took a given mass of water, you measured the change in its temperature, and you used that to calculate the amount of heat that was there. So let's review the experiment, or a more traditional calorimetry experiment. You had a sample. What did you guys burn? What did they have for you on Tuesday? Okay. So you got your burning snack, right? And you try to capture that heat in a given sample of water. And you measured the change in temperature with a thermometer. Okay? So in this case, the M was the mass of water. The C was the heat capacity of water, which is always 1, so we don't really deal with the C part very much. And then the T is the change in the temperature of that water. You put those together and you get heat, or energy. Okay? So let's try some of these. So let's say you had 400 grams of water and it raised in temperature from 23 degrees C to 51 degrees C. And we could say how much heat was produced, or that's the same thing as saying how much energy was in the chip. So what we do in that case is we say, all right, Q equals MC delta T. So Q, the heat, or which is the energy in this case, is equal to 400 grams of water times 1 for the heat capacity, so we won't worry about that. We're going to worry about the difference in temperature, which is 51 minus 23. Okay, so that's 400 times 28, which equals 11,000, what? 200? Yeah. And that's calories, little c calories. Okay? And that's exactly what you did. When you do the next part, the real calorimetry with the bomb calorimeter, actually, hang on a second. I'm going to go get one so you can calorimetry, and here's why. So a real calorimeter is this big metal thing that you actually immerse in the water. That gives you a much more accurate temperature reading. It's your thermometer. Because you don't have to worry about the heat being dissipated to the air. It's actually in the water, so all the heat gets dissipated out into the water. And you can actually measure that. Inside the calorimeter, you have your sample. And because it's all enclosed and underwater, you have to feed oxygen into it. So we pressurize it with oxygen. So that, remember, I don't know if you had this issue on Tuesday, but in some of your designs for your calorimeters, it wouldn't burn, like it wouldn't stay on fire because the oxygen couldn't get in. Well, with a bomb calorimeter, we avoid that by pressurizing it with oxygen, so forcing a bunch of oxygen in there. Then we know it's going to have all the oxygen it needs. And we ignite it with a little wire. And you actually have a remote trigger so that you just push a button on a thing that's connected by the wires and it ignites. The problem with this, or not the problem, but the thing you have to do with this is realize that you still have a heat transfer issue because some of the heat heats up the calorimeter itself. It's this big metal thing. And so some of the heat from your burning sample is going to heat up the calorimeter, and that's not going to make it all the way into the water when you measure the change of water, because you have to bring both the water up to a different temperature and the calorimeter. So in that case, the total heat is going to be the heat that you measure. I'm just going to leave the T out of there, or the C out of there, plus the heat that's used to heat up the calorimeter. And each calorimeter is different, so you actually use a known sample and a known amount of energy to first standardize the calorimeter, all this stuff. You guys aren't going to do that. We'll get these numbers from another class that does these standardizations. But the reason I show you this is that when you're doing these measurements of heat or these experiments about heat, you have to realize that you have to account for every little bit of energy, where it might go, what it might heat up, and that can potentially change your results. So just be aware of that when you're doing these, as you found out on Tuesday, the only way you can really get good, accurate results is if you really account for every little bit of energy that that burning sample is producing. And that's how you can accurately measure it. Okay. So the last thing we need to talk about is fuels. We're going to talk a lot more about fuels in the next coming weeks and months, including your biodiesel that you made. So what makes something a good fuel? What are some properties that a good fuel should have? Should have what? Stability. Yeah, absolutely. Let's say dynamite might be a pretty good fuel, but you don't want a bunch of it in your car, right? So the stuff must be pretty stable until you want it to then, right? So let's do let's add to that a little bit. Stable until you want to use it. A piece of granite is pretty stable, but that's not a good fuel either, because you can't get the energy out of it. It's just stable, it just sits there. So this is a good, okay, so great, that's a great part. What else? What else do you want in a fuel? Sure, strong, from the molecular standpoint, yeah, strong bonds. What about, like, I'm thinking more just a bulk property of a substance that would make a good fuel. Yeah, let's say energy density, which is energy per amount. Whether that amount is in grams or liters or whatever. You want something that has a lot of energy in a small amount of stuff, in a small amount of matter. Something like Fritos aren't great energy for your car because there's not that much energy for a mass of Fritos compared to something like gasoline. So these are some major important points of fuel. And in fact, you really can't do better about these with these factors and strong bonds and some of the other things than fossil fuels. What are fossil fuels? Yeah, anything that comes from old organic matter. So things like coal, oil, natural gas. Fossil fuels are very stable. They've been sitting under the earth for millions of years without doing anything. So they're certainly not going to do anything if you just have them around. Right? You can have a huge pile of coal. Nothing bad's going to happen. It's not going to spontaneously blow up or something. Then they have extremely high energy density. In fact, there are very few substances on Earth that have the energy density of fossil fuels. And think about that in like your car. You've got a gas tank, right, of 13 gallons or 18 gallons of whatever, and that can propel that giant car with giant people and giant stuff in it for, what, 300-400 miles, something like that. That's a lot of energy. And you think about something like the electric cars that just came out, like a Chevy Volt, can go about 40 miles with a battery pack that weighs way more than a tank full of gas. So that gives you, and that's the highest tech battery materials basically that we can make right now. And you only get a fraction of the energy that you get from fossil fuels. So this has been the big kind of sticking point in moving to other renewable forms of energy, is you just can't get that kind of energy density. So let's look at it from an energy standpoint. Why are these substances so high in energy? What is going on there? Remember, we said that energy isn't free. It can only be transferred. It can't be created or destroyed. So how did this stuff get so much energy in it? Yeah. And then an animal ate it. Right. And they both decomposed. Okay, so there's a couple parts there. First, you had all these animals and plants doing respiration, photosynthesis, eating stuff, growing stuff, whatever. So that's taking in a bunch of energy. And then there's a second part too that you alluded to. Right, because if it were just that, then burning dead things would be a good fuel, right? Every time I don't know, you go out in the woods, you find some logs and you put them in your car and burn those, or you find some dead rabbits and you burn them. Like, that's not a great fuel because it's just not as dense. Now, I mean, you could do that. You can run a car on burning wood or rabbits or whatever, but it wouldn't go very far. It wouldn't be very dense. So part of that is, over millions of years, the compression of huge amounts of earth on top of these things has concentrated that energy to a very, very dense form. And so these fuels have basically the energy, energy has been being put into them for millions of years. And then, of course, it comes out immediately as soon as you burn it. So that's one of kind of the problems here. They're so dense in fuel that the stuff that we invent is almost never going to approach that. And we can try with some catalysts and some chemical processes like making biodiesel, and maybe we can get close, but that's always going to be an issue. What are the major fuels used for? So, like, let's take coal. What's a good thing about coal? I mean, as an energy use, as a fuel. What's good about it?
It's easy to store.
It's easy to store, right? It's solid, so you just can make a big pile of rocks and you got some coal. Easy to ship. Put a bunch of it in a train, move it around, or in a boat. What else? What? Yeah, it's very energy dense, and we have a bunch of it, right? The U.S. is filled with coal. We have to blow up and destroy all our mountains for it, but we can get it. It's here. What are the drawbacks of coal as a fuel? It's dirty, pollution. What?
Destroys the mountains.
Yeah, destroying the mountains, destroys the people who have to actually get it out, right? You have to get miners to go in and have pretty horrible lives to get that coal out for you. And from a fuel standpoint, it's not really dense enough to drive something like a car. So coal is very energy dense, but not nearly as energy dense as gasoline or oil. Are there coal-fired cars?
There was.
There were, yes. There were steam cars where you'd have to like shovel coal into the boiler compartment, and then it would boil water and produce steam and drive the car that way. But the gasoline is so much more energy dense that it's much more efficient to do it that way. And what about natural gas? What do we use natural gas for? To heat our house often, yeah. Yeah, you can actually use it in cars. This year, I believe, there are going to be some cars coming out in the U.S. that can use both natural gas and gasoline. Why is that important? Why would they do that? Yeah, right now, natural gas is incredibly cheap in the U.S. And it all comes from the U.S. And you know why that is? Anybody heard about this new technique? Yeah, the fracking, right. So natural gas was pretty price stable. Actually, it was going up in price over time as the fuel became scarcer and scarcer. And then a few years back, they developed this process called hydraulic fracturing, which suddenly allowed us to get gas out of places that we never could before. So let me see if I can pull up this picture. Here we go. So what you do is you actually put a well, a big tube, way down into the bottom of the shale rock in the Earth's crust, which we knew there was gas in there, but we didn't think there would ever be a worthwhile way to get it out, because the gas is all stored in these tiny little fissures in the rock. It's not like normal gas mining. You find a pocket of gas, of a bunch of gas, and you pump it all out. Okay, and in the shale, the shale rock, there's no big pockets of gas. It's just tons of tiny little pockets of gas all over the place. So you put this big pump down there, and you shoot down a bunch of water, like an incredible amount of water, sand, and chemicals, and you actually bust out all these fissures. So you're cracking all the rocks. It's called hydraulic fracturing or fracking. You're just manually like blowing apart all of this rock under there with tons of water. So about 200 tanker trucks full of water. Pump that stuff down. And then when you bust all these little cracks up, the gas can come out, and you can collect it. And then ideally, you also collect the wastewater and the waste chemicals coming back out and go out and treat them. So this has made gas freely, I want to say freely, cheaply available and domestic. Right? So in places where infrastructure is already set up for natural gas, like power plants and heating and that kind of thing, they've seen prices just drop dramatically. And there's other good points to this too. Natural gas burns much more efficiently than coal or gasoline. So we're actually, for the first time in a while, the U.S. is substantially decreasing our greenhouse gas output because of this. But there are some problems too. Has anybody heard of issues with this?
The water that you get out of it is toxic.
Yeah. You're basically pumping all of these toxic hydrocarbons and toxic chemicals into the ground, using it to blow up these cracks, and then hopefully getting most of it out. And the thing that frightens me about this, or I don't want to say frightens necessarily, but is potentially not good, is they haven't really done science on this yet. It's fairly new, and the companies have sort of just done it, and they figured, well, we'll study it at some point. So a lot of people are really concerned that they're being poisoned by this, and there's a good chance that they are. What? Yeah, so places like Pennsylvania and Ohio and where there is a lot of this stuff, a lot of this shale, there are big, big political fights going on about what should be done here. It has the potential to bring in huge amounts of money to states with really struggling economies, but also potentially poison everybody. So, and people who have the land actually get to lease the land for this drilling. So if you have a bunch of land that's over this shale, you stand to make an incredible amount of money if you have the mineral rights to that land. So it's a very contentious thing right now because you have people saying, well, I need this money, and then you have other people saying, yeah, but we're all going to be poisoned. So, so the science is being done, and a lot of people want to. It's more a philosophy of what you do. A lot of people want to stop this and say no fracturing until we find out that it's totally safe, and then other people say, well, we should do it and study it, and then if we find out it's not safe, we'll deal with it then. The other part of this is, of course, it's a commercial enterprise. So the companies, the gas companies, won't release the actual names of the chemicals that they're using because it's proprietary information of they don't want other people using their special chemical blend to do the fracking. So that has some health implications as well because people don't actually know what's being put into their shale. There have been some good movies about this lately. There's one called Gasland. It has a pretty striking pictures where what happens is the stuff tends to have the potential to contaminate the groundwater supply. And in some of these areas, like in West Virginia, people are actually have flames coming out of their faucets and their sinks because the gas is mixing in with the groundwater. And they actually have this in this documentary where you'll see people like turning on the faucet and they can literally light the water that's coming out of their faucet. It's just burning. So anyway, keep your eye on this stuff. There's a lot of good information going on. This would be a good source of articles for your article things. Look up some stuff on this. There's a lot of good information out there, and it's going to be a huge thing in our future because while we benefit from the cheap domestic energy that it produces, I think we have to be really careful about potentially ruining all our groundwater supplies also.
Is there any concern about the stability of the ground, or is that layer of rock just not any, is it just too far down to make any difference on the stability of that actual ground? I'm just wondering.
Yeah, I don't know that one. I would imagine it's pretty far down. I think the issue is more that it collapses into the groundwater, which is below it. So yeah. And the concern really is just in the transparency and the regulation. That in a lot of places they're sort of just doing whatever they want because there's no studies, nobody really knows, and there are a lot of industry groups out there saying basically it's fine. We haven't proven that anybody got poisoned, so we should just keep doing it.
Would it be held accountable if they prove that they're going to get poisoned for it?
I don't know. We'll see. Other questions about this? Okay. Well.